This is St.Pete.net Meetup. I am John Calloway. Clayton Hunt's behind the camera. We've got Kevin Wolf here doing IoT. Please be sure to find us on Meetup and join the discussions on the discussion channel. Follow us on Twitter and YouTube and anywhere else. We're always looking for great content and great speakers. So if you have any suggestions for that, just let us know. So with that, Kevin.
Thanks, John. Oh, how's everybody doing? Looks like a nice comfy spot out there. So as John said, I have to figure out where I can stand here to see everybody. I guess kind of a unique environment. Anyways, I'm Kevin Wolf. Here's a little bit about myself. President of Software Logistics. I've been a Microsoft MVP for 9 years. Can everybody hear me all right? Can anybody not hear me? Raise your hand if anybody can't hear me. Good. Can anybody see that? It's a little small on here, but hopefully we'll be able to talk through most of this here. Microsoft MVP for 9 years. Does everybody know what an MVP is? Just basically a cheerleader for Microsoft, and we're kind of good at what we do, so they recognize us for our contributions, for giving talks and stuff like that. So it's really it's really an honor, and I'm really happy to be working with Microsoft in that. Early background in electrical engineering, embedded systems development. For the past 10 years, I've been focusing on mobile development. I'm currently developing a product called IoT App Studio. IoT App Studio is a web-based development environment for building IoT applications where the focus is on coding rather than configuration. There's some of my contact information. Before we get into my talk, I want to talk about a really kind of exciting event that I was at last week. So how many people in the room have heard of Softworks, S-O-F-W-E-R-X? A couple hands in here. Oh, Kelvin, join, thanks here. How about SOCOM? Anybody here SOCOM and CENTCOM down in McDill? A few hands on that. Has anybody not heard of them? Okay. SOCOM is basically a big organization down. How about special operators like Navy SEALs and stuff like that? Anybody not here? Okay, cool. So basically SOCOM down at McDill Air Force Base manages all those type of people. Softworks is a local company, really exciting. I encourage you to check them out. They actually provide an interface between the operators and SOCOM and the general public and I guess academia and industry. Last week I was involved with a Thunder Drone event, and previous to that they put out a request for information about how can we counteract and how can we kind of like get in front of the threat of drones that are being proposed or kind of being sent against our troops over in the Mideast. And what they want to do is they want to be able to kind of come up with a solution before it becomes a real problem, kind of like the IEDs type of situation. So what they did was they said, does anybody have any of this type of technology? They did that last month. We submitted something to them, and we were actually chosen as one of like about 70-some teams to be able to present our technology last week. So what we presented was a technology to be able to integrate all sorts of these different types of sensors out there that collect information about where drones are in the world and kind of what type of drones they are, with the equipment that actually will shoot them down or shoot a net at them or somehow disable them and get them down. So the reason why I bring that up is that it's a really incredible experience. I get to meet a lot of very, very interesting people. But that application that we built was something that we built with IoT App Studio, because breaking those things down, it's the sensing stuff is IoT, if you think about the messages coming from it, and also the stuff to shoot the kind of drones down is also IoT. So our product was used to be able to kind of communicate between those two things. We'll find over the next couple of weeks, I guess, if we'll be able to kind of make it the next cut, but it was a very interesting experience. So again, IoT App Studio, we talked about that a little bit. Fun fact about me, just like many of your pets, I've been chipped. I've got a 800-byte NFC tag implanted in my hand. You can kind of see what it looks like right there. It's really kind of neat. This was actually getting it injected. Kind of interesting story on that is this is the kind of little thing in there. It's about the size of what they would do to extract blood when you actually kind of go to the hospital and kind of give blood type of thing. But we put it in there, and then we couldn't actually push this little plunger thing down, if you can see that little kind of green dot on there. And the reason why is we had this little plunger guard on there, so it was sticking in my hand for about 5 minutes while we went on the internet trying to figure out how in the heck do we actually inject that into my hand. It really didn't hurt, but it was kind of a strange feeling that thing's just sticking out of my hand, just waiting to be injected in. Got a little tattoo on the top of it. It's an NFC chip out there, so you can take your Android phone or your iPhone phone, put over the top of it, and be able to read information out, and it gets you to basically my website, my blog. Some other uses for it might be unlocking doors or anything that actually reads NFC. So again, NFC is just a technology that by itself doesn't have any power, but when you actually put something on top of it, it actually energizes the chip and then starts sending out, in my case, 800 bytes of information from the chip to the actual NFC receiver that pulls the data out and does stuff with it. So it's kind of neat. It's kind of in there permanently, especially, at least with the tattoo now. So anyways, for our talk tonight, what is IoT? It's kind of a loaded question. Our conversation tonight can be broken into 3 parts. The first part is talking about devices and sensors, because without devices and sensors, IoT can't exist. You hear a lot of these companies out there saying, hey, we got this great platform for doing IoT work, but without the kind of the core pieces, devices and sensors, you really can't have IoT. Gateway is optional, but in some cases you need to have those devices talk through a gateway to talk to the cloud providers out there. And finally, the cloud, which adds value to the devices. Make sense so far? And as we go through this, any questions that come up, I really like kind of interactive discussions. So as we start going through this, I really appreciate any questions and talks as we go here. So yes, sir.
How long have you had the NFC chip for?
How long have I had it for?
Yeah.
Probably about 1.5 years now, I think. It's been quite a while, yeah.
That's really fascinating.
I was a little worried about infection on that, but I knew a medic that was from the Army, and he knew how to do that stuff, so I'd give infusions. So it was a little, I had a couple shots before that. He didn't have anything, so he was totally sober, but I had to kind of rattle my nerves a little bit. So any other questions? Yes, sir.
Some questions on that?
Yes.
How well does it work? Do you have to be like really close
You
to the
do,
sensor?
actually. That's a really good question, because a lot of people think that, can people track me now? And maybe with some super secret NSA type equipment, they might be able to do something like that. But with your standard Android iPhone, you have to actually put it right on top of it. And even with an Android phone, you have to kind of know where the antenna is placed, so you get the antenna right on top of it. So with a lot of NFC, they normally come on stickers, and you have to come within about 1 centimeter. But this one just kind of, it's a little bit in there, and it's not quite as powerful as some of the stickers with the antenna on it. So you have to get the antenna just like right on it, and then your phone will just go beep, 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 and bring some data in. So, question.
The second question, can you reprogram it?
Yes, that's another excellent question. So there's different types of technologies that are out there for this type of thing. There's NFC and then RFID, okay? So our RFID, I think, is probably more prominent on, like, for pets getting chipped and stuff like that. And basically all RFID is something similar to this, where again, it doesn't have any power source on it. You put something on top of it and it energizes it. But RFD is like a one-time code in there, so it just reads some serial number off and you can relate that to some foreign key. This one is an 800 byte, basically read-only, I guess read-write memory that's in my hand like that I can put anything on it. There's different type of formats of packets that you can put on there. And my website's only like maybe 24 bytes or something like that. But most NFC readers just read the first one out of there. So what I can do is I can put all sorts of different data points on there, and if you have the right type of application, you can see what's in there and actually open that up, like the different ones. But most of the time when you just like hook out your Android phone, or if anybody has a Windows phone in here anymore, no. You did? Yeah, we all got them, we just don't use them anymore, right? As a Microsoft guy, that's a full sore spot because I got my own iPhone here too, but anyway. But yeah, so really you just kind of put it on there and it'll pick up the first one on there and just show what the data is on that. So, any other questions? I love talking about this stuff, so just feel free to chat. So anyways, we're going to talk about devices and sensors to start with. Then we're going to talk about the gateway, which is sometimes needed to be able to get your device and sensors to the cloud. And then finally, we'll wind up talking about the cloud. So that's kind of what our conversation is going to be organized, how it's going to be organized tonight. The agenda, what is IoT? Talk about the cloud, gateway devices, as we talked about, what type of technology is involved with it, security, challenges, and then questions and answers. And as I said, if anybody has questions as we're going through this, I really love just kind of talking about the stuff in general, so please feel free to just raise your hand and we'll take a little tangent and discuss stuff. So let's start with devices and sensors. It's a very large category. I mean, it's a lot of things kind of fall into that. They provide an interface between the physical world and the digital world. They can be thought of as 2 general types of categories, sensors and actuators, where sensors actually sense things in the real world and actuators act upon them. Quick example of that, sensor would be something that measures temperatures. Actuator might be something like servo, or something that actually will kind of push something forward or something like that. So that's an actuator. Some devices can live in both categories, and they can be standalone, where they have their own intelligence and business logic associated with them, or they can be part of kind of a bigger network. The conversations that these kind of devices have with the computers is really the basis for IoT. So again, the sensor can do stuff by itself, sensor actuator can do stuff by itself, but to really make it interesting, it has conversations with other computers or the cloud, and those conversations, like I have on there, is really the core of what IoT makes. Digging into sensors. In its most basic sense, like I said, sensors take stuff in the real world and turn that into a digital signal. In some cases, in a lot of cases, that's some type of analog signal that's being pulled in, converting to digital, and that's really kind of the starting point of where sensors go. Some different types of that would be temperature, humidity sensors, light sensors, motion sensors, location sensors, things that detect whether things are open or closed, a flow rate sensor, something that measures the level on a battery, weight sensors out there. Just a quick show of hands here. How many people know what an Arduino is? So just kind of know what my group is. Oh, good. We got a lot of people that know that. How many people have done stuff with IoT where they've actually built a sensor and actually pushed it up the cloud? Okay, so we got a few people out there. Okay, good. So it's going to be a great talk for you guys. So anyways, these are different types of sensors that we have out there that measure something in the real world. It can be an analog signal like a voltage type of thingy, or light, or all sorts of different type of things, and then convert that to a digital signal like it's pushed up to the cloud. So there's really three different ways that these sensors work. One is to produce an analog signal, just a pure little cheap analog signal. The next is to produce a primitive digital signal, and then finally to produce a smart digital signal. And we'll get into what those are in more detail in the next few slides there. So we'll start out by talking about an analog sensor. Does anybody here know what a thermistor is? Got a few hands out there. So a thermistor is something that measures temperature out there, and that's an example of what we're talking about here as an analog sensor. So the sensor that turns something into a voltage, and then the voltage is actually measured by some type of device out there which turned into a digital signal out there. So resistance and ohms, we're not going to get too much into double E talk tonight, but the way a thermistor works is as the temperature changes, the resistance and how well electricity can flow from one end to the other changes. And what we can do is we can actually measure what the voltage drop across the resistor is, and based on the voltage drop across the resistor, we know what the temperature is. So that's how it converts something in the real world to an analog signal that we can measure. Voltage is a unit of measure. I think everybody knows what that is. There's both AC and DC voltage. AC is what you would have out of the outlet there. DC is kind of the battery that starts your car, or the batteries in this type of device. So most of these sensors actually are DC. The actual output of them is DC, which is just kind of an interesting point. And they're usually very, very inexpensive. So these thermistors that we're talking about, very, very small, and really you can buy them on Amazon for maybe 5 of them for $5. But if you actually bought them in very, very large quantities, you're probably paying less than a penny for them. So these are things that are very, very small, very, very cheap, and they're in a lot of different types of things out there. So once we have this voltage drop across our thermistor, we need to be able to read that. Computers don't do very well working with analog stuff. They need something called an analog to digital converter, or A to D converter, that senses how many volts that is, and then actually turns that into a series of numbers that a microcontroller can actually take and say, okay, I'm measuring 3.798 volts on there. That's going to be the equivalent of, just we'll say some number in the process here, of 3,427 or something like that. And based on that, we can actually go ahead and say that 34,700, we apply a factor to that, and then we can turn that 34,700 into a real time temperature. So that's kind of how we go from these cheap little analog sensors that are changing the resistance with respect to temperature to a raw number, to a scaled number that can actually represent a temperature. Does that make sense to everybody? It's kind of the core building block of how a lot of sensors work. So if anybody has any questions, I know this is new to a lot of people. So yes, Kelvin.
How do you measure the lifespan of those types of sensors?
The lifespan of them? That's again, that's a really good question, because a lot of times those types of components last for a very long time. I'm not sure I can give you an exact answer on that. What I can tell you, however, is that those are really kind of solid state. Kind of showing my age here. People probably don't even know what solid state is anymore, but the idea is that there's different types of kind of sensors and electronic components. That's a component that doesn't have any moving parts. It's very, very static. It's just a little piece of silicon in there with some wires on it. So something like that lasts for a very long time. There's data sheets that'll tell you how long these things last. I don't think thermistors would ever really go bad. And if I'm going on too much of a tangent, let me know. But to answer your question, kind of a slightly different way, little light bulbs, if we knew we had the little flashlights from a very long time ago with a little filament in them, those had not an expiration date, but they had a limited lifetime because there was kind of like a filament that we ran current through and it got really, really hot. Those things expired. Those are being replaced by LEDs, which again would be kind of gets considered more solid state in that it just kind of energizes stuff and lets light shoot out of it, so they last pretty much forever. I mean, we're talking hundreds of thousands of hours on LEDs. So I don't know if I answered your question properly or not, but data sheets, if you have something you're concerned with, a lot of these types of technology, you don't even just talk about that because they just last for a very, very long time, longer than you and I will probably live. So but that's cool. Any other good questions though? Any other questions? Going on? Yes, sir.
You mentioned Arduino. Being
Yes.
a Microsoft guy, have you used NetDuino?
NetDuino, yes. That's a neat product. I don't know if anybody's really using it anymore, but NetDuino is a really cool technology, and I built a quadcopter with it once, quite frankly. So NetDuino is like an Arduino. So if everybody, the question was, do I know what NetDuino is? NetDuino is something that basically lets you run .NET C# code on an Arduino type of device, a really small device to be able to program. So if you don't want to program in C, you can program in C#. Unfortunately, I don't think they're really kind of selling a lot of them anymore, are they? But it's a really type of neat thing because the way it worked is you have a really, really cheap microcontroller, a little $3 device with a few components around it, and you were able to run C#.NET code on it, do some really incredible things that, like your network stack, Arduino on network stack. I guess there's libraries you bring in, so it makes it relatively easy, but there's really interesting stuff you can do with that. So NetDuino's a neat little product out there.
So for someone like me who's thinking about getting started in some stuff like this, knows some C#,
Right.
NetDuino versus Arduino, any suggestions?
Yes, NetDuino probably not, and we can talk afterwards if you want a little bit here, but something that you might want to look at is Win10 IoT Core. It's a Raspberry Pi device that runs Windows that you can run C# programs on it. So it's a really type of thing. It's a very, very capable platform. The neat thing about that is you can run .NET applications on your desktop and then get them working there and then put them on the Raspberry Pi. So it's a really cool product. So that'd be something to look at. We can chat more about that later if you want. Any other questions? Cool, good stuff. So again, analog sensors are things that are really, generally really, really cheap. The output of them is going to be some type of DC signal usually. There might be some other type of signal that would be emitting out of it. And need an analog to digital converter, which is usually a microcontroller, which is a very small version of a microprocessor, which has a bunch of stuff on it, which again would be a talk in and of itself for a couple hours. But microcontrollers are very cool. The NetDuino platform and even Arduino run on microcontrollers. An example of that would be a thermistor. So the next type of sensor that we're going to be talking about is primitive digital signals. And what's really interesting about these devices are little black chips that provide some type of combination between mechanical and electrical stuff. An example of that would be an accelerometer. So how many people have drones out there? How many people fly drones? Cool, we got a few hands out there. So one of the things that makes a drone fly is you need to figure out kind of like the attitude or the orientation of the drone. Is it like this, is it like this, is it like this? And to do that, use something called an accelerometer and gyro, which we're not going to get into the details of those. But the way those things work is they have like little kind of very, very, very small microscopic kind of mechanical devices inside them, which actually measures kind of the orientation and kind of forces that get applied to something internally there that kind of all consolidated. So it's got internally these types of really cheap really cheap analog sensors, but it also has some type of electronics and controllers inside it that will do some signal processing and massaging of the data. So when I talk to that device, I can talk to it at a slightly higher level. So instead of having an analog signal coming out of it, I have a digital signal coming out of it. And I guess another example would be, everybody knows that there's probably an accelerometer in your phone, so when you move it around, it can kind of detect where you're at, and a compass and those types of things. So there's also the MEMS types of devices in here. Yes, sir?
I was just going to ask that. You had analog sensor or MEMS. Like, what's the difference between the two?
has an internal analog sensor or MEMS. Yes, 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 yes. So MEMS, it would be, like I say, something that is mechanical, that just has like some type of really fine microscopic stuff in there, and then there's stuff around it to be able to measure forces or magnets, and we could talk about that for one other thing. But the difference between this and an analog sensor that would be producing a primitive digital signal, I guess an example of that would be another thing from a quadcopter, which quadcopter is very interesting from the perspective of understanding how this stuff works, is some of them have like either LiDAR, which will actually detect how far you are above the ground and shoots the laser and counts all the way back, or even like some sonar type of devices where it puts a ping out and then sends it back up again. So those don't necessarily have any of these microelectronic stuff in there, but what they do is they actually have things that will actually read maybe like light or how long it takes for like the signal to come back, and then it's going to do some internal processing to produce more of a digital signal.
Okay, and that's still different from an analog.
What's that?
That's still different from an analog sensor, like it's kind of like a light sensor or a.
Yeah, so light sensor would be an example of that too. It's something that would measure like
Okay.
light and turn that into that. So,
Got
yeah, I mean, it's kind of it's really when you start talking about that. I mean, even like when you talk about MEMS here, that's when you break it down to its kind of purest form. Those are analog sensors.
Okay.
So, I mean, because the little magnets in there that, or the little things that read the magnetic force on there. So
Yeah.
when everything comes down, it's analog at a real super level, but then it kind of gradually goes up from
Okay.
there. So I hope I answered your question.
Yeah,
a
you
little
did.
bit. Good. So anyways, so the output of this is going to be something in ones and zeros. So talking to your microcontrollers out there, it's a little bit faster and easier to talk to because it's already doing the preconditioning of the signal to be able to know what these readings are. And in the case of some of these more advanced type of sensors, they may actually go ahead and even tell you what the angle is. So for instance, when you're talking to a lot of these really cheap components, they don't really have a lot of computer processing power on it, so it'll just give you like a number between 0 and 1024. Can anybody tell me why 1024 and not 1000? Come on, let's see some hands here. All right. Cool. If you don't get it, look it up sometime. Ones and zeros are fun. Ones and zeros are fun. So yeah, so basically it'll give you a range between 0 and 124, and then again you do the conversion factor to be able to turn that into a raw heading or attitude of whatever you're measuring. Some of them may actually tell you that we are at exactly 37.2 degrees, and that would be the output of it. Like the LiDAR type of devices, basically that's something that shoots a laser down and then figures out the time in flight back and forth like that, and it'll tell you how far you are above the surface very, very accurately and very, very quickly, obviously. Something like that's going to have more microcontroller, micropower on it, so the output of that probably isn't going to be something between 0 and 1024. It's going to be something like 37.2 inches or 37.2 centimeters or something like that. These signals usually can't travel very far. They're not meant to be kind of dispersed between a device over there and a device over there. They're usually kind of sitting on the same circuit board as a microcontroller. Microcontroller can be used to kind of condition and process these signals because a lot of them are relatively noisy. If we kind of go back to the accelerometer example in a quadcopter, there's a lot of different forces acting on that. So I'm going to be sampling that accelerometer maybe 400, maybe even 1,200 times a second, reading all the data back in and doing some averaging and filtering on it between like the range between the starting and the end point on that. So when I get the raw digital signals coming back, there's going to be quite a bit of noise on there, and there's some techniques to be able to do filtering on there. And a microcontroller have multiple of these sensors, just like on your phone right now. You probably don't have a microcontroller in there, but in the microprocessor in here, there's a whole bunch of different sensors that are communicating on there. So that kind of makes sense between the really primitive, kind of cheapo analog sensors and these primitive digital sensors. Kind of makes sense. We're talking still at a very, very low level. All this type of technology that we're looking here is really pretty much standalone and can't do anything by itself. I guess a little bit more about primitive digital signals. There's different types of kind of technology that's used to be able to connect these things up. One wire where the data being sent to the chip and the data being received to the chip comes on the same line, and then we just have some timing patterns where it says basically for 30 microseconds the microcontroller will send something down to the actual device itself, and then the device itself says, oh, I just got something, so the microcontroller goes into what's called a high impedance state, which isn't terribly important, but basically the microcontroller goes into receive mode where the actual device here can send something back up to the microcontroller. So we're using one wire to connect this device from this device, and that's called one wire technology. I2C, which is inter-integrated circuit, intercomputer, I think it's called. Anyways, I2C is also another very popular kind of technology for communicating between microcontrollers and different types of devices out there. With this type of technology, there's one master, which is usually the microcontroller or the microprocessor, and then there's multiple devices or slaves out there that it talks to. And the way that works is the master says, I want to talk to a device at address 0x37, and it'll say, okay, device 0x37, I'm sending you something, and then what'll happen is device 0x37 will send something back to the microcontroller. It's all working on one bus, and if you know anything about electronics, you can't necessarily send two signals and the same line at once. So the way it works is either the microcontroller is talking, all communication starts with the microcontroller, and the microcontroller says, okay, I'm going to start asking you for something, and then I'm going to shut up and start listening. I'm not going to transmit anything on that, because if the microcontroller and the device talk on the same line, there's going to be bad stuff happening, and you won't be able to get anything back. So in that case, like I say, the microcontroller talks to the chip saying, hey, give me some data. The chip goes, oh yeah, I can talk to you back. It's actually got two wires, and can anybody tell me what the second wire is used for? The first wire has data on it. What would the second wire be used for? Yes, sir. Ah, not quite. Anybody else? Yes.
Ground?
No, that's kind of the opposite part of it. Yes? Yes, sir. You got it? Clock. There you go. So these things talk really, really, really fast. Well, relative, I guess, do you think 400 kilohertz is fast? It's pretty fast. So anyways, these things talk relatively fast, and what we need to do is actually synchronize the data between the microcontroller and the device out there. So we have something called a clock. And the clock is basically just a square wave that goes and as the clock signal transmits between this device and this device, the signals from this device and this device are synchronized with the rising edge and the falling edges of the clock to be able to make sure that we are sending kind of data back and forth. Does that make sense? It's kind of a relatively important topic when we start talking about some of these low-level protocols. Now we have a data line and a clock line. Yes, sir. I'm sorry, what?
Are the peak and the shroud important?
Well, usually they're just between 0 and 5 volts that we care about. So we're really not talking about AC to signal at this point. It's usually just a square wave. So yeah, that makes. Any other questions?
Is data sent on both the uptake and the downtake?
It can be, yes.
It can be,
yes. Well, I guess the reason why I say that is because data, and that's actually that's a good point that I don't think I brought up here, that we send a series of data spikes kind of going when it's up like this and down like that. The 5 volts or 3.3 volts represents 1, and the ground, as John pointed out there, represents 0. So as we see the clock coming through, we actually see is the data being transmitted 1 or 0, 5 volts or 0, associated with the clock points, and then we can say, okay, I got my clock, I need to see is it 1 or 0, 0 or 5 volts, and based on that, it'll pull that data signal out. We're talking about serial communications. If we know the difference between serial and parallel, we're sending 1 bit out at a time. Good point, thanks for bringing that up. So again, we got inter-integrated circuit, which I think might be actually inter-integrated computer, I can't remember. Anyways, it's something like that. I2C is how it's always referred to as. The final one is actually serial peripheral interface. So I2C is actually the typical clock rates you see there are like 100 to 400 kilohertz a second. It sounds like a lot, but when you're actually getting 1,000 readings in a second, you actually have, that's not really that fast. So we have something called serial peripheral interface, which is similar to I2C, except we have one clock line, and we got one data line that's going between the device and the chip, and then another data line that goes between the chip and the device, called MISO and MOSI for lack of what they're called anyways. And the idea behind that is it's much, much faster. We can start looking at megabit transmission rates between the two, because what we have in that case is we have like dedicated lines between the two, and again, we have the 2 lines and then the actual kind of the clock that synchronizes to the things out there. The other thing that's kind of interesting about SPI is usually SPI has a 3rd line that goes from the chip, where I2C sends an address out saying, I want to talk to device 0x37, 37 hex. Where SPI, they usually have some type of chip connect, some type of interconnect between the microcontroller and the actual processor itself to say that this is the device I want to talk to. So it actually, what's called interrupts the device saying, this is the one I want to talk to. And so just like each one of the devices would have a line to it from the microcontroller to the device. Can that make sense? And again, you don't necessarily need to know the details here. Just I think it's helpful to understand when we start talking about IoT, how these things work at a real base level. So when you start thinking higher level, you kind of understand what these things are happening below the surface. Two options for getting data from the device. One would be where the sensor interrupts the microcontroller, and the other is where the microcontroller pulls the sensor. And the difference between the two are very, very significant, actually. So with a quadcopter, what you want to do is, as often as possible, you want to go ahead and pull data from these different types of sensors and get them into the microcontroller and actually start doing some averaging on them. Because like I said, they're noisy, and the more samples you have coming in, the better type of sampling that you can do and the better type of reading that you can get for everything on there. So what you want to do is anytime that data is available, you want to be able to go out and grab that. With some of these types of devices, the conversion time can range on there depending on different types of circumstances on there. So the actual device itself can say, hey, I've got data for you. Go ahead and ask me for it, and I'll send it as soon as possible. So it actually interrupts the microcontroller and it grabs it as soon as possible, and then it can start the next conversion cycle. That's how I can get these things going very, very quickly to pass data back and forth. The other way is that the actual microcontroller pulls the sensors. So in some cases, you may not be able to put enough wires between all these little black chips on your circuit board and the actual microcontroller itself. So in that case, what you'd have to do is have the microcontroller say that, I know that within 20 milliseconds, that conversion will be done. It might be 5 seconds, it might be 6 seconds, but I know it's guaranteed based on the data sheets that the conversion will be done in 20 milliseconds. So we can set up a loop on there that will say, okay, every 20 milliseconds, you go out and ask for the data. So in that case, the microcontroller pulls the data, it pulls the data, and pulls the data. So it makes sense. And that's actually kind of a relatively important thing when you start kind of thinking in the IoT world. Am I going to be able to get the data as soon as it's available, or can I pull it? So kind of makes sense.
Is the interrupter similar to like a RQ sort of?
Yeah, that's exactly what it is. Yeah, basically what'll happen is you can write an interrupt handler, and those have to be really, really fast, because what happens, I guess the question is, an interrupt handler the same thing as an IRQ? Yes, it is, basically.
Okay.
And what you can do is, with the way those things work, is you tie lines between the microcontroller and the actual kind of chip itself, and then it'll send a signal up to the microcontroller, and it'll run a really, really small piece of code that will go ahead and grab the data and get back into what it's doing. Because basically what an interrupt handler does is it interrupts the microcontroller. I'm doing all sorts of work out there. I'm talking to the network over here. I'm doing this thing over here. I'm doing that thing over there with the microcontroller. I get this interrupt coming in. It's going to put all that stuff, push all the stacks, and do everything that I need to be able to create or recreate the state of where the microcontroller was prior to the interrupt coming in, do my work, and then go back to my everyday kind of business. So interrupting, you have to kind of really think through your software. Writing interrupt handlers is something you got to do that's very, very efficient.
So like another example of like interrupting, would that be like kind of like a keycard swipe? Would that be the same thing or no?
The only reason why I'm hesitating on that a little bit, I guess you could think through that. Yeah. If you actually brought it through there, yeah, there's probably something. There's a couple different ways that would actually work. The keycard swipe itself would actually have like a little microcontroller in it. And then as you're putting it down there, it's maybe saying, oh, I'm seeing something, I'm seeing something, I'm seeing something. It's waking up the microprocessor and sending it. So in and of itself, it is an IoT device. As when we start talking about the next class of devices here, there might be interrupt handler stuff built into this little chip itself. So yes, that's kind of a good example. Yeah, as it's swiping it through, interrupt, interrupt, interrupt. And interrupt wouldn't necessarily be, I've been swiped, because at that point, the whole activity's done. So that. But as I'm swiping, oh, swipe, yeah, each one, yeah, good example, thank you. So really, that's the difference between interrupt and polling. And I guess to your example too, the way the card swipe thing works, it probably isn't something where you swiped, where you swiped, where you swiped, where you swiped. It's actually going to not really interrupt in this case, but it's going to basically send a message to somebody else. And that's slightly different than an interrupt, because we're kind of talking at a slightly higher level, but it's that type of concept though. Any other questions? Great questions so far. Really good questions. Smart digital sensors. These are generally self-contained types of devices out there, so we have a fair amount of computing power in there. They may actually contain some primitive digital sensors and some of the less than primitive ones like we just talked about internal itself, but it's generally going to have some type of microcontroller in there that pulls all that data and does something interesting with it. These really come in two different types of flavors, two, I guess, bigger categories of flavors. The first flavor would be UDP and TCP devices, transport of the internet, plug them into Ethernet, and it's putting packets back and forth, telling you what's going on. There's all sorts of other different kind of protocols out there. Serial RS-232 is, I guess it's still pretty common, but it's used to be very, very common. RS-422-45, good for long range type stuff. These are just kind of different protocols and different types of data that sits back and forth. Zigbee and Z-Wave are very, very popular in home automation right now. Power line interface signals, that's said some type of signal on the carrier of your power line. That will get pulled out. How many people had X10 in here? X10? No X10 people. You got
Used
one
to.
X10
No,
people?
Used to.
Yeah, so X10 is, yeah, used to, exactly, that's the right word on there. We got Insteon now, but, well, Kelvin, you got some Insteon stuff, don't you? Yeah, so X10 is kind of an interesting technology. It was out a very, very long time ago, and it wasn't very, very reliable. So I'd say probably about the fifth time where the lights all of a sudden lit up in our bathroom at home at 3 o'clock in the morning, the wife said, "It's going, you can't have X10 anymore." So replace that all with kind of newer technology, Insteon and smart things, and it's been a lot more reliable. But PLI, the reason why I say that is PLI is basically something where I plug it into the wall and it injects a signal on top of the AC that will be able to send signals back and forth. Bluetooth, everybody I'm sure has heard of that. That's a very, very popular type of protocol. And then finally USB devices hardwired in your machine and push data back and forth really, really fast. Make sense? So those are smart digital sensors. So we start talking about TCP, IP, UDP devices. These devices are generally smart and have some type of microcontroller on it. Talking TCP is not easy. Talking things like Z-Wave and Zigbee and those types of things, basically I stream bytes out with some header packets. But talking those types of protocols, I guess one might argue UDP isn't that terribly difficult, but generally speaking, compared to some of the other protocols, TCP and UDP, they need a little bit of horsepower to be able to kind of read and pass data over the line like that. Generally a little bit more expensive. They can be Wi-Fi, Ethernet, or even cellular. There's a company out there called, they developed the Spark and the Electron, and basically what that is, it's really neat, Particle, that's the name of the company. So Particle has a little chip out there. It's a little, kind of basically the size of an Arduino. What's really neat about it is for $70, you can actually get one of these, and then you can pop a SIM card into it, and all of a sudden you have something where you can put anywhere that you can get cell coverage to be able to send messages from that little device to really anywhere because you're on the internet. It's not that terribly cheap, but a lot of times if you're just sending like very, very small data at kind of not a very fast interval, you can do a lot of different stuff with it. So for instance, I think it's like for $2 or $3 a month, you can send 1 meg of data, which doesn't sound a lot, but if all you're doing is sending messages when a door gets opened or when some type of motion trigger gets sensed like that, you can actually send a lot of data and use that. But like I say, the interesting thing about this chip is it's similar to an Arduino, but it's got a little kind of a SIM card in it. Plug it in, and basically you got IoT device anywhere. I'm actually using it on my boat up in Hudson right now to be able to track the GPS on it, and track the battery voltage on it. And like I say, it just works. I got a little solar panel on there that keeps a little battery charged, and it's just free IoT except for the $2 or $3 a month.
What's that called again?
It's Particle IO makes it. Particle IO is the company. I think Electron is the one that actually has a SIM card that fits in it. They also have the Spark, I believe it is, and the Spark is one that's Wi-Fi, but it's the same type of technology, and that one's obviously free. Yes, sir?
So your device on your boat, does that like send you a text message alert if it moves when you're not expecting it to?
It should, but it doesn't right now. Basically, it just sends it right now. Like I said, I have IoT App Studio, which is something that at a super high level, it just reads lots and lots of messages in and then archives them and does some interesting stuff with it. In this case, it's just archiving that data. But yeah, that would be something that would be really good on there, is to say that if my boat's moving right now, I would get a text message because I'm sitting here and it's up there. Yes?
What's an example of something where you'd be okay using UDP and dropping packets?
Yes. So anything that's time-based, anything that if I get data from like 3 seconds ago, it may not matter. Where I used that was from a quadcopter because TCP is a little bit heavier and you got to send more data with it. I'll give you another example too, but in that case, it's like, you know what, I want to have data so I can populate the screen to get the attitude so I can draw stuff on there. I don't necessarily care that I lost 2 packets ago because I'm looking at live data. I guess the question was, I should repeat that, where would using UDP be acceptable in that UDP isn't like a guaranteed delivery like TCP would be? Another example of that, a buddy of mine is doing fleet tracking. And as we just talked about, sending data packets over cellular is relatively expensive. I mean, it's all relative, I guess, right? Sending 1 megabyte for $3 a month. You have lots of devices that got tens of thousands of devices, that really adds up. If I can send UDP and I can put some other kind of checks on top of it where I'm going to ensure that I'm getting the packages. So for instance, if I'm sending a message up and I'm putting a sequence number with it and it tells me I dropped one, then I can use a cheaper protocol, and cheaper in terms of bytes being sent up. If I'm getting billed by bytes, I can kind of put my own kind of guaranteed layer on top of it, or at least tell me it's missing, and I may care, I may not care, but at least I'll know. Does that kind of answer your question?
Yeah.
But again, that's a good question, realizing that UDP is not something that guarantees delivery, and where would you want to use that in something in the IoT space? Again, it just depends on the problem you're trying to save and the costs associated with it, so on. So, good question. They can be either Wi-Fi, Ethernet, or cellular. What these devices special is they can connect directly to the cloud. Sometimes the language or these protocols you speak aren't compatible and they need translation, which we'll talk about on the next slide here. But another type of example that kind of where we're using, now we're using TCP on that, but a device that we created before I was telling you about this thing we did for SOCOM. Part of our example was actually putting a Raspberry Pi, software-defined radio, SDR. Anybody knows what that is? A couple people, cool. So basically it's a block that you can plug into the computer and you can look at all sorts of frequencies and pull all sorts of data from the air out there. So aircraft have transponders in them. The transponders actually send things like their heading, their altitude, maybe their tail number, their flight number, and altitude or latitude and longitude and so on. That information is being just kind of squawked out over a transponder. You can buy one of these SDRs and hook software-defined radios. It's just a $25 USB device. Plug it into Raspberry Pi running Linux, put an antenna on it, and at that point you can pull all this tail number, the altitude and stuff in from the cloud, from like the radio waves out there, and all of a sudden you've got something that's, I think, very powerful, which will tell you where all these aircraft are out there. We took that device and we actually turned that data into a message and then sent it up to our IoT App Studio app via TCP IP on there. So again, in that case, we're sensing something in the analog world, which is just these radio signals, and turning it into something we're sending up to the cloud. So that's really kind of the sensor part. Before we move on, any questions on sensors at all? Kind of give a high level there. So again, without devices and sensors, we can't have IoT. So now let's start talking about actuators. While sensors measure things on the outside world, actuators act upon it. Actuators, again, can be analog, primitive, or smart. An example of this would be like an on and off type switch. The relay, something that turns a LED or a light on based on the output from a computer. So the output coming out of a computer is very, very low current. It really can't do a lot of work with the outputs coming off of it directly. If you try to hook up like one of these light bulbs to just like the microprocessor lines on your computer, you'd probably fry the microcontroller because it's going to try to pull so much current through the pin that's driving it that it'll probably just fry the internal circuits on it. So by itself, it can't necessarily talk to that light bulb and turn it on. It needs to use something like a relay to be able to open and close a current source that's going into it. That makes sense. It's kind of a really, really important topic of why we need actuators as well as sensors. It's something that takes, like I say, the very, very low kind of milliamp output that we can have coming out of a microcontroller and turns it into something that we can power, maybe a 50-watt light bulb or anything like that. Okay, makes sense there. Servos are also another thing that we can hook up which actuates things in the real world. Servos use something called pulse width modulation that actually sends kind of a square wave out, and the kind of the distance between the square wave will actually say what the servo will actually rotate to. It's kind of new technology. And back to our quadcopter example, the ESC, the electronic speed controls, uses pulse width modulation to say how fast do I need to bring that kind of that propeller so I can stabilize it. The whole objective, obviously, with quadcopter is to be able to keep it nice and stable like that. Inherently, it's going to bounce all around like this, so you need to read sensors really, really, really fast as you can, filter out as much of the noise as possible, and then send the signal out via pulse width modulation as quickly as possible when I get the data coming in from like where my orientation or attitude is to try to stabilize it. And that's kind of the complete cycle there where I do all the fun math using all sorts of neat algorithms to be able to get the inputs from the sensors and then eventually send pulse width modulation to these ESC or electronic speed controls. We'll see how fast the propellers spin, which will move the devices up and down. Make sense? Cool. Device summary. As I mentioned, without devices, there can't be IoT. Sensors monitor the real world, actuators act upon it. By definition, IoT requires some type of protocol like UDP or TCP, because really that's what we're talking about. Internet's in the word of Internet of Things. Unless the device natively speaks one of those things, you'll need some type of gateway to translate. And even with some TCP UDP devices, you may want some type of gateway between the actual device itself and the cloud that you'll be sending data to. Yes, sir?
If a device is on a delayed read, is that still considered IoT, like it only gets read once a month?
What is defined as IoT is a very, very loaded question. I would say yes on that. As long as we're doing something, even if we're basically a delayed read or even like archiving over the month and it batches the data up,
Yeah.
I would kind of consider that IoT.
Okay.
Just to kind of build on what you're saying there, when I first started hearing this thing called IoT, it's like, you know what, I did embedded systems back in early 1990. I did IoT back then. It's like, well, yeah, I did embedded systems and I connected some of these things together, but I really didn't necessarily, I don't think I know what I know now. I would really consider that IoT because it was just kind of a standalone type of system. So defining what IoT is still a little bit nebulous, but I think it's, and we'll talk a little bit once we get to the cloud area, what I think some of the things that the criteria are that would make an IoT type solution. So gateways. You can think of a gateway as similar to being a router. Gateways communicate with the sensor actuator and translate that data and forward it up to the cloud. A gateway might be a small computer that connects a number of TCP devices. A gateway may also have custom hardware that usually are like transceivers that have radios in them that communicate with things such as Zigbee, Z-Wave, or Bluetooth devices. And it's possible to chain gateways. So what do we mean by all that stuff? Basically what we're talking about is that a lot of these types of smaller devices, obviously we're going to need some type of microcontroller in the world to be able to talk to any of like the MEMS devices, the really kind of primitive digital or analog ones. But once we start talking about a little kind of higher level type of sensor, we still may need some way to be able to get that up to the internet. For instance, Zigbee and Z-Wave, they're really good in this type of environment because they really scale from the perspective of the types of devices you can have on there, but they don't talk directly to the internet. You need to have some type of, in this case what we're talking about is some type of transceiver or radio inside the actual kind of gateway hub device itself that plugs into the internet. So does anybody hear of something called Smart Things? Smart Things is a technology out there that's used for home automation. And Smart Things actually has a Zigbee and Z-Wave radio within it that will actually talk to all these different types of devices using all sorts of different protocols and then convert that over into TCP/IP and either process it locally or send it up to the cloud. So again, the important thing here is to understand that these devices, these little $9 motion sensors that you can get off of Amazon that can talk Zigbee or Z-Wave aren't something that can hook up to the internet directly. You need some type of hub to be able to make those things talk. And again, the final point on there is it's possible to chain these gateways together. So it's something where you may have all sorts of like mesh type technology in your house. So we have these little hubs that have little radios in it that talk to like maybe the sensors in this room here, and then they would be chained to another hub somewhere else to be able to communicate messages back and forth. And those could either work independently or push them up to the cloud. Gateway security. So another thing that's important about these gateway devices is if you buy these little devices off of Amazon, like we'll just say a motion detector, that's a nice simple one, $9.99, you bring it as part of your network out there, they may not be all that smart as far as who they can talk to. So to be able to put them on the network, I press a button saying, I'm going to bind to you, and they set up some type of protocol and talk back and forth. But when you do that, they're not very smart as far as being able to know like what part of network that I'm on, or that I'm part of Kevin Wolf's house on Lago Vista. They actually use the security in the router itself. So the communication is actually established by the sensor and the device talking to the gateway, and then the gateway handles all the security as far as talking to the internet out there and talking to Kevin Wolf's account out on SmartThings out there, if that kind of makes sense. And when you buy these little types of devices, they aren't necessarily something where I can go in and say, okay, hook up to it, and I'm going to type my username and password in. So the security is really enforced by either saying, okay, I need to bind this guy to this guy, and now they have their little dance that they did, and now that they can talk back and forth, and they can be part of the network. Or you just basically plug it in and say, this is the device that's hooked up, and you're using physical means to be able to secure these types of devices. Most of these devices also don't encrypt data, and they just send it in raw text out there. It's pretty relatively easy to be able to kind of pull data from Zigbee and Z-Wave type of thing, but I guess you may not care that your motion detector went off. So let's see, gateway security continued. So again, we talked about the different mechanisms for securing them. They can't necessarily talk directly to the cloud out there with the security in that. We need to be able to be them part of the network. Provide a trust mechanism, talk to the cloud, and then authentication restricting by IP or MAC addresses, requests being signed with an access key type of thing. So we're actually providing different levels of security depending on kind of where we're at in the food chain on the gateway process. That kind of makes sense? Gateway communications. There's different types of communications we can have out there. Some popular ones out there if you're actually doing some IoT work from a custom development standpoint as opposed to just kind of like integrating in your home automation equipment. Some would be like MQTT, message queue telemetry transport, and AMQP, which is just kind of an updated version of that. MQTT's been around forever, where AMQP has a whole other set of kind of security and complexity that goes with it. Two-way communications where the devices communicate with the server, and then the server can communicate with the device, kind of both ways like that. And then another part of that is publish and subscribe architecture, where I want to listen for all messages coming in with this type of data, with this type of signature on it, and then I'm going to publish with this type of signature on it. So basically, the server's acting like a clearinghouse where I'm publishing with maybe something that says ATT001, and then anybody that says, I want to subscribe to ATT01, it'll actually pull the data down and bring that with it. They're good for chatty and kind of more complicated communication protocols, something where you actually have to have real-time data going back and forth. Is it a little warm in here, or is it just me? It's just me? It's sweating up here. So anyways, so good for chatty, more complicated communication protocols. Message queue protocols. So one thing that's interesting about these is two-way communications. We'll talk about HTTP in just a little bit, but HTTP is more of just like a one-way post. So I'm sure a lot of people in this room have heard of something called REST, where I submit data up. That's just kind of one-way post, which we'll talk about in another couple slides here. But in these cases, these are things where I need to provide two-way communications, where not only do I have to post something to the server needs to communicate back to the device. And again, with the publish subscribe type architecture messages. The difference between MQTT and AMQP. MQTT is this very lightweight and relatively easy to implement. So if you have like a small little microcontroller without a lot of programming space in it, you can't put really sophisticated programs in it, MQTT might be something good for you. If you have something like a Raspberry Pi or more advanced types of device with a little bit more advanced technology, it might be a good protocol. AMQP is obviously a lot more secure, so if security is a concern, you definitely want to look at something like AMQP as opposed to MQTT. Yes, sir?
Where do the messages queue? On the gateway or on the device, or how does that?
So it really depends on something called quality of service, and we can have a good conversation about this too. But so depending on what type of quality service you can have, there's like a best effort where it'll shoot it once, and if it's like doesn't get sent up there, it'll basically just kind of sit and just kind of disappear after a certain amount of time and not try to resend it out there. And then the other thing is like quality service too. If you send a message up there, it'll just try to send it. It's guaranteed to send it at least once. So it'll queue it actually in the device itself. And then quality service 3 is it'll send it exactly once. With quality service 2, the handshaking isn't quite as extensive, so it could send it multiple times because it really didn't know if it sent it or not. Where quality service 3, there's enough handshaking where it's guaranteed to send it only once. But it'll actually queue it up in the actual device itself in the MQTT software, so not in the gateway itself, so more in the device. And I guess that was your question, was it queue it up in the device, not the gateway.
Okay.
Yeah, the thing that's actually implementing the MQTT protocol. There's a whole set of handshake that goes back to make that work. So, cool. Any other questions? Cool. And again, MQTT is something that you may have on your little Arduino. There's actually an MQTT stack for it. I do not believe there's an AMQP stack on it. It's a little more advanced, and I don't know if it would fit on most Arduinos. So HTTP is kind of another protocol where we can send data back and forth. In this scenario, if your device only needs to phone home, where it's basically just saying, I'm going to post data, I'm going to post data, I'm going to post data, I'm just going to post a message up there. You don't necessarily have to have two-way communications on that. Examples of those might be temperature sensors and motion detectors. Temperature sensors are going to say that, okay, I just need to post the temperature that I'm at, which is probably about 85 in this room right now, up to the server, and then it just kind of logs that. It doesn't necessarily, other than maybe confirming that I got it, there's no real two-way communications possible there. Motion detector, same type of thing. Post it to the server and then basically log it or do some type of actions on that. Other than maybe saying that I got something, saying I've acknowledged it, I've get it back, so I don't need to send it multiple times. There really isn't two-way communications on there. It is possible, however, that in some cases you may want to be able to send a message to the server and the response coming back may be something slightly more than just like a 200 OK on it. It might actually send something cloudy associated with it, saying that this is a JSON packet. So for instance, maybe my temperature sensor is hooked up to a thermostat in a house, and it's going to post the temperature every like once a minute. Maybe one of the times it posts it saying, okay, you need to change your thermostat level to 73 degrees instead of 82. So it's possible to send data and then maybe send some data back down to the device afterwards. Message queue protocol, let's go forward. Devices implement a listener, so again, two-way communications is not possible out there. One of the interesting things you can do with these HTTP devices is you really don't know if the device is online or offline. With some of the MQTT and AMQP protocols, you can have some type of heartbeat kind of built into the actual message queue stuff itself saying that, yep, I'm here, I'm here, I'm here, and you know that the device is continually hooked up. With HTTP, you don't have that because it's just a one-way communication, unless you're doing some type of web sockets, which is a whole other talk. But what we can do in this case is set some type of timeout saying that if I don't call in within every 5 minutes, I may have a problem with me. So some type of watchdog on the server saying that, yeah, I'm expecting a call, I didn't get one, somebody needs to go out and take a look at that sensor. So that's something that we can do. Most of these are really only sensor devices, and I think you can see why that makes sense in this case, because remember, actuators act upon the real world, sensors actually update data. So in this case, if I'm actuators act upon the real world, sensors send data up to the server. So if I'm just sending data in one direction, it's a sensor generally. If I need to be able to take action on it, in most cases, HTTP is probably not what you want to do to be able to communicate with it. Make sense? Cool. Local intelligence. So not only can gateways do things as far as kind of like message buffering and kind of protocol translations and all interesting stuff to take these Zigbee and Z-Wave and push it up the cloud. They can also do some things as far as providing some type of business logic. The way smart things work is you actually go ahead and you write programs saying when this sensor does a certain thing, I want to perform these types of actions on these type of actuators, like turn on a light, blare some music, turn on an alarm, those types of things. In some cases when you write those programs, that program runs in the cloud. So what happens is the sensor sends data to the kind of the Smart Things hub. The Smart Things hub forwards that up to the cloud. The cloud figures out what it needs to do and then sends a message back to the Smart Things hub and then talks to this device over here. Another way that the gateway works is for things that need to be a little bit quicker or really aren't as complex. The actual sensor talks to the hub, and then the hub does all the logic in here because it's got a little computer in it, and then talks to the device up there. So that's kind of another thing that gateways can be used for, is to have a little bit of local intelligence and functionality on there. I mean, how to report state to the servers. Yeah, so in some cases it's basically it's sending data. I can do stuff locally, I can do stuff locally, and then there might be some type of threshold where I need to log that data. So some stuff happens locally in the processing, and even part of that local processing, it's going to take that data, some threshold happens, and push that up to the cloud. Gateway summary. So again, devices may be cheap and not very smart. They may not be secure. You may have a lot of different devices out there. The gateway is responsible for communicating from the devices up to the cloud. For a complex system, the gateway needs to be very, very scalable, because if you think about it, if I've got like 500 different devices out there, and if all the messages are going through the gateway, that's where your bottleneck is going to be. So it has to be pretty smart. There may even be some stuff on there saying that's send every 5th message because it needs to scale. Gateway may be as simple as a dedicated computer, or gateway may have additional peripherals such as transceivers and other mechanisms to be able to communicate with these sensors. So now to the third part of our conversation, which is starting to talk about the cloud. The cloud is really where makes the IoT interesting, and where I think it differentiates the stuff that I've been doing in the early 80s when I was doing my electrical engineering hat, designing circuits and kind of putting firmware on top of them, from what we're doing today. So one could say we've been doing IoT for years, where we've been doing embedded systems, fixed purpose little device that I worked in the scale industry. So basically electronic scales, taking readings off there, weigh bars and stuff, measuring the shear and the strain on the devices and turning that into numbers that people say how much the train cars weigh or whatever. So fixed purpose device, scale hooked up, and it's just displaying 7-segment numbers what the weight is on there. These were sometimes connected with some type of controller out there that says, okay, we consolidate all these weights from these different weigh bars into one common controller out there. And these were self-contained networks. So it's a lot of the same concepts that we're talking about IoT, but in this case, what we were talking about is like a self-contained network. We're using some stuff with like RS-422, 485 that tied like maybe 5 or 6 different scales together to a common kind of house out there that actually had the printer in it that had like printed out the bill weights and so on for the different type of material. So if you think about it, it's the same types of things that we're doing right now with the Internet of Things. However, the scale was much, much smaller in that case. So that kind of makes the difference, kind of distinction between building a self-contained kind of network of little devices and building something that has thousands upon thousands of devices pushing data in it. When I think IoT, I kind of think of almost the second scenario. So cloud could be a public, it could be a public cloud such as Azure, AMS, or Bluemix out there. It also could be in a data center. It's really the thing that makes the IoT solution out there is something where I'm consolidating data from all the sensors into some kind of common server on the back end. So the cloud responsibilities, they need to be able to implement some type of listener for messages coming in. Message queue based ones like we talked about earlier, MQTT, AMQP, with managing all the messages coming in. HTTP server, just listening for messages coming in on basically some type of REST server out there generally. And then finally just listening on a socket for raw TCP or UDP messages coming in, and then being able to filter or pick up the data from that. If you have something that needs to communicate in real time and pass a lot of data, that's kind of a good way of doing that, because you're as close to the device as possible. It's just the best way to be able to pass binary to back and forth. It's a little more difficult to implement, but if you want to get real good scale out of it, that's probably the way to go. So the trait of IoT is the actual concept of scales, and really what differentiates what we've been doing in embedded systems for a very, very long time. Supports thousands or even millions of devices. Reliable messaging is another big part of it. You want to make sure that if it is important for your system, which needs to be able to send messages where you can't drop them, you need to have kind of protocols in place to be able to make sure that you have some type of handshaking back and forth, so if the messages don't get sent, you retry them. Sometimes you can do that with the MQTT or the message queue protocols. Sometimes you have to put another layer on top of it to be able to handle that. But again, not every time you need to have reliable messaging. Sometimes if you're just looking at real-time data, what happened 30 minutes ago may not be interesting. It may be, it may not be though. So maintaining in-memory state makes this difficult. So one thing, if anybody's done any type of real high scalability programming, one of the challenges, one of the real things to make that not work so well is keeping data in memory. Because if you're managing 200,000 devices, we'll say 200 million devices or something like that, if you have to put like maybe 20 bytes for each one of them, that's a lot of data that you need to keep in memory. So you need to have some mechanism to be able to handle lots and lots of devices, and keeping all those in memory generally isn't the best way to do that. The entry point into the cloud needs to do minimal work. So what we mean by that is where the actual messages get sent from the device and get picked up by the listener, whatever it is for the kind of in the cloud there to be able to process the data. That's really your bottleneck, because there's ways of being able to, like using load balancers and stuff, to be able to have multiple listeners listening for messages coming in. But generally, that's going to be your bottleneck because the processing, if you use some type of queuing technique, once the data's in, then you can dump it into a queue and get picked up and processed by other type of things out there, and you can scale that horizontally fairly well. But the point where stuff is coming in is generally going to be a lot of your bottlenecks on that. So the interesting things about messages that get sent and forth, because messages are really kind of the conversations that these sensors and devices have with the cloud, is that they have really three parts here. The who, what the device, and then the what, the type of data that's sending, and finally the content that actually goes with it. So let's go look at some examples of that. The who in this case is going to be room number 300, and I'm a temperature sensor. I know that. The what is the temperature changed. In this case, the payload that I would be sending would be 78.5. Feels like the air conditioner came on, so it might be a little cooler now. So anyways, there's a couple different ways we can send that data up to the server. The first one is the JSON here, which represents something very easily that we can read. Device ID, room 300 temperature. So it's going to be the device ID is going to be the room 300, the temperature. The type of message that we're sending is the temperature changed. And then finally the payload that goes with that is 78.5. I don't know how many characters that is from here to here, but we'll say maybe about 75 or something like this. That's a lot of data. And we talked earlier, if I'm using something like UDP and I'm paying for each byte of data that I send back and forth, that could get expensive if I'm sending a lot of things back and forth. Not only that, if anybody knows about kind of like how parsers work and things out there and how computers work under the hood, turning this into raw data needs, you got a big string coming in, so I need to parse that as quick as possible. Newtonsoft or whatever kind of JSON parse you use is really pretty fast. However, it's still, working with strings is not something you want to do on a high scalability system. If we look at the second set of messages here, we can encode the same set of data into 1, 2, 3, 4, 5, 6, 7 bytes. So not only is that a lot less data that we're processing or sending through the UDP packets out there, UDP packets, it's also something that the computer can very, very quickly kind of use a state machine to parse. Oh, I know what the first one is, the message type, oh, an FE message. I know that that's temperature change, 4301. Oh, that tells me that it's temperature sensor in room 300. And then the next 3 bytes might be the actual data, and then the final is like something that says, okay, this is the end of the message. You have some checksums and stuff on there, but that's in there. But I think you can see that from a high scalability system, sending this message is so much quicker than that. Make sense? Cool. Example number 2, room number 300, motion detector. In this case, what we're saying is that the motion detected or motion stopped. And for this type of message, we don't have a payload associated with it. The actual message itself is what we're using to be able to identify the actual kind of the payload itself or what the message contained. So over here, we actually had to send a payload to say what the temperature changed. In this case, we're actually sending 2 different types of messages. One is motion detected and motion stopped. In this case, we can just say who I am and then what, so it's very, very quick to be able to send the data back and forth. Kind of makes sense on how the messaging works. And of course, in this case, we just have one type of piece of data in our payload there. For a lot of type of message, you would have dozens or potentially even hundreds of data pieces that come with each message on there, but in this case, we just have one. Acknowledging messages, that's an important part before, like we talked about earlier. Reliability is important in a lot of cases for IoT. It just makes sense in a lot of cases for a lot of things in computer science. So the internet is reliable but not perfect. There may be many hops that go between the analog sensor out there that's actually reading temperature 78.5 until it hits the cloud. Failures do occur, so for critical data, the device may require an ACK or the server to say that, hey, I got your data, you can kind of wipe that from memory and not send it again. So if data is time critical and a retry sense might not make sense, that data is going to be stale and you don't want to resend it again, the UDP thing that we talked about earlier. TCP might make that a little bit easier because there's a whole other layer on TCP that actually provides reliable messaging. But UDP is cost less in terms of complexity and bytes on the wire, so that's something where you need to think about where it's not required. So some of the challenges associated with the cloud scaling, that's one thing, like I said, that differentiates what we're doing now compared to what we've been doing over the years in embedded systems. complexity. It must be able to handle thousands, if not millions, of devices. So it also must handle lots and lots of devices, but also may handle those devices sending messages every few seconds very, very quickly. So throughput, those messages must be processed very quickly as well. So like we talked about before, we want to take those, read those in, ingest those messages as quickly as possible, and then dump them into a queue for processing. So one of the challenges with that, like we just talked about on the previous slide, is acking the message. I've got my message coming in, and I want to be able to read it and then basically queue it off and do processing later. But I don't necessarily know that that message was valid. So there's some of the things you need to think through when you're building a scalable system, is that at what point can I say that I know that I got this message and I can go ahead and ack it and say that you can remove it from memory because I got it. So thinking that process through as far as when it needs to be processed. So writing this type of software isn't necessarily something that you want to write. That's where Azure and AWS and Watson come in. They can provide a lot of services that make that stuff go really well. It's better to scale horizontally across this way, adding additional servers on there as opposed to making servers go faster, because eventually you won't be able to find a faster computer, but you'll be able to kind of put computers horizontally and build out a very wide network for processing messages. And again, parallel processing, or better yet, public cloud that has its stuff built in. So I think that where the cloud comes in is where the ultimate value of IoT exists out there. Business intelligence, once I've actually pulled all the data in, then I can do some type of analysis on it, some big data, and some type of really just kind of looking for trends and so on over time. Obviously, lots of different things you can do with that. Control system, so the other part of that too is I'm pulling data in, and then I can act on that by sending messages to completely unrelated actuators or some type of mechanism to be able to basically put some corrective action in place if it needs to. Business intelligence, so data is uploaded and processed. It's usually archived, looking for trends over time. You can put it in a relational database, but it could scale. Do you have a question, or you're just stretching?
Yeah, stretching.
Okay, that's all right. So looking for messages over time, basically looking for trends of data over time, predictive maintenance, and so on. Put in a relational database, but there's some other techniques out there using like NoSQL type document-based type systems, or flat storage out there to be able to put the data in, something that makes it go a little bit quicker and scales a little bit either. It's not reasonable to watch every data point as it's coming in. If you have something that's sending data points in every 5 seconds to get 200,000 devices, you can't look at each one of them, so you kind of have to look at it over time. The other part of that too is when you have this data coming in, put some triggers in place so that if I got certain conditions coming in, I don't necessarily act on every data piece, but if I'm seeing some exception values coming in, then I can take action on those values. Control systems, like I say, the other part of that is when I see something coming on and happening in the real world out there, I can pull that data in, then I can put some corrective action in place, some type of maybe predictive maintenance and so on. So summary, without devices, IoT can't exist. Devices come in two flavors, sensors and actuators. Some devices cannot be connected directly to the cloud. Some devices need to go through a gateway or protocol converter. Cloud services is where IT value can be optimized, and in most cases, cloud needs to be highly scalable in terms of both device management and throughput. So basically, I got lots of devices out there, so I need to manage devices, and I also need to handle lots of messages coming through there. So any questions? Covered a lot of topics here. Hopefully that gave you an idea of some of the different kind of conceptual ideas that you need to start thinking about when you play in the IT space. Cool. Yes?
Oh, yeah, one question. So the compressed messages, those are...
Compressed, you mean the binary ones? The second
compressing to
yes.
the, yeah. So
Okay.
you show the JSON example and you compress it to binary.
Yes.
Is that compressed message then sent up to the cloud to be processed at a later time, or does the gateway process that message and send it up as like JSON to the...
It really depends, because just to give you an example, bringing it back to SmartThings, SmartThings uses the binary protocol, or excuse me, some of these Zigbee and Z-Wave devices send the binary protocol from the motion detector and these really kind of really cheap devices to the hub, and then the hub will do some stuff on them. It may do it locally, but it may convert that to JSON before it sends it up the cloud.
Okay.
So it really kind of depends.
Okay.
Yeah.
Alright.
That kind of answer your question?
Yeah, it does.
Okay. Yes, sir.
We're gonna learn more about
I'm sorry, what?
Where can I learn more about the
Windows on Devices site, and just look up Win 10 IoT Core. It's a really cool thing. So you're a Windows developer, C# developer, I'm assuming. And you do any type of UWP work, Universal Windows, writing Windows 10 applications?
mostly
Okay, cool. Yeah, so it's the same C# type of thing. So yeah, just look up windowsondevices.com or just look up Win 10 IoT Core. Basically what it is if you have like Raspberry Pi 2 or Raspberry Pi 3, what you can do is you can get a micro SD card and you flash it with a Windows image and then you put it in there. And if you have a touch screen, it's basically a little dedicated device where you can write C# applications that will run on it. So it's really neat. Yeah, like webcams and all sorts of stuff like that. If you know what Cortana is, you can actually use Cortana on it.
It's free.
What's that?
It's free.
It's free, yes.
It's Microsoft.
They're giving a lot of stuff for free now, they really are. They're giving pretty much everything for free. Yeah, there's a version of it if you actually want to build a device, a commercial version of it that you would license. But if you're putting it into a device, you probably want to look at that anyway. So, yeah. But the version that you would be using, yes, it's absolutely free. And if you want to turn it into a device, then you would love to work with you to be able to figure out how to do that. Yes, sir. It's Calvin.
Are you going anywhere tonight to have more of a deeper talk for people that are interested?
Absolutely, yes. We're going to be going to, I believe, Hofbrau House afterwards. Is that where we're going? So afterwards, we're going to Hofbrau House to have a beer or two, and we can carry on the conversation and chat about all sorts of stuff. Yep. More questions? Yes, sir.
So a lot of what's the development platform for a lot of this? It's not .NET, right? Do people develop that?
You can. It really depends because when you're developing for this, there's so many different parts of IoT, which we really didn't even talk about IoT development because we kind of get a conceptual baseline here. It really depends. If you're writing like some of the small devices that might be C, just writing real super low level C, and then you're using some type of compiler and then burning it on Z-squared on the little $1 Arduino. Or if you're doing Arduino, there's a language called wiring, which is a C-like type language that it's really pretty easy. So it kind of abstracts away a lot of the memory management stuff and C that you really have to worry about when you're building embedded systems. When you're working in the Linux world, Python is a pretty popular one for doing a lot of the embedded systems programming, so that's one that you would use for doing that. If you're working on the cloud side, that's any type of cloud technology that you may know. I guess some people use Node, some people write some of their stuff in Java. I do a lot of my stuff in C#. Node.js is obviously another player for writing the cloud stuff, so it really depends on the problem you're trying to solve. Do you have anything in mind that you're thinking of, or
I'm
just in general?
just wondering what, if you were to learn this, what would be like, where would you start? So you said
So-
C#, is that under like SPNet Core?
It is, and just commenting on this.
Yeah, I'll say, go with whatever one is most comfortable for you, because pretty much, especially if you're starting to learn now, just go with whatever one you already know, and then convert to something else if you need to.
Right, that's a good point. Yeah. So if you're starting with an Arduino, you're kind of limited on the type of technology that you're going to be using. You're probably going to use this wiring, the C-type language. But once you start working on the cloud side, like Kelvin says, if you're a Node programmer, you can use Node for that type of thing. So there's that type of thing. So it just depends on where you look at. When I said earlier that there's a difference between embedded systems and the cloud IoT type stuff, embedded systems is really kind of where the sensors and the devices and all those types of things live. And like it's kind of one of my points that I put in here, without devices, IoT can't exist. But I've also got to claim that unless you're doing something with the cloud up there, you're not necessarily doing IoT. I'm not saying that's a bad thing, and don't get me wrong, if you're not doing IoT, you're still doing some very incredibly interesting and powerful things with an Arduino. But if we're looking at the problem that we're solving and the skill set and the things we're bringing to bear to be able to kind of build a solution, the thing that I'm using on this Arduino separately is very different than when I'm thinking about this whole big IoT picture. That's why I think it's important to understand, am I working on IoT, or am I working on Arduino, or am I working on something that processes messages really fast? Yes?
And then I can chime in that if you work on Azure IoT Hub solution, Raspberry Pi, and the Raspberry Pi you can do Python, Node.js, JavaScript,
Yeah.
C++, C, C#, whatever works. So if you start in IoT, probably easier to go to a Raspberry Pi, or Kevin could agree.
Yeah, so I guess one of
That's
the...
a nice starter platform. That's the whole idea of Raspberry Pi. It's a nice starter platform to start get the feel of that, because there's sensors they can attach to Raspberry Pi that might use Python to write or Node.js to do versus going deep into the C language like Arduino
Yeah.
and whatnot.
Yep, exactly. That's a very good point. Thanks, John. Yeah. So I guess what you're saying there is, if I'm working on the real low-level quadcopter stuff and the real twiddling the bits and flashing these LED kind of strips back and forth, maybe you got to live in the Arduino world. What John's saying is, as an introduction thing, maybe you don't want to start in the Arduino world. You want to start in something you're more comfortable in. And again, with the Raspberry Pi route, you got a couple different routes with that. 110 IoT core, C#, or just your Raspbian Linux distributions running on a Raspberry Pi, which is a Wild West, which is really kind of cool, actually. Any other questions? Yes?
What is, what was it, IoT Studio, or what gap does that fill?
Oh, my product?
Yes, your product. Yeah.
Yes, thank you. So what my product does is it really kind of puts a layer on top of some of the great tools out there. So as I mentioned before, that it's really difficult to write high scalability software. And Microsoft and Amazon and IBM Watson's product, they have a lot of really, really great services as far as high scalability. What my product does is actually sits on top of those that lets people kind of work at a kind of more in the problem space. So instead of figuring out, okay, I need IoT Hub and I need to link it to this other type of services, you're saying, okay, I've got these types of messages and I need to process these messages and do these things with them. And I'm really kind of not worrying about what type of technologies under the scenes to be able to do the message processing and how to link the stuff together. So it's really just a way of being able to construct orchestration of messages that will happen in a very fast and reliable way, as well as device management and kind of the whole package on that.
Sort of the business intelligence end of.
The business intelligence, yes.
Is that sort of business
Yes,
intelligence
exactly.
end of the process?
I'm sorry, what?
That's
Is
what I
it?
was asking.
Yes.
If it's the business intelligence end of the whole process.
Yes.
You got all your devices collecting data, just how you view it, how you organize it.
Yeah, exactly, those type of things and what type of actions it can take on there, and just like simple scripting type stuff.
Will you show a little bit of that?
The product?
Yep.
I don't want to turn this into a sales talk, but I certainly don't mind. What time do we got? He's going, well, maybe not. I get 2 minutes. Yeah, I'm standing between you guys and beer, so I don't want to do that too much long. But I'll just give one quick screen of it, and then we'll move on. Okay, so I think
tickets
For
Raffle.
oh, you
okay. So I think you can see the screen on there. So, oh, you can't see the screen because I guess I got cut off. So that kind of answers the question, huh?
I
guess
think
it
it's
wasn't
still
meant to be.
it's still on the presentation screen. Did you just
Well, how the heck? Do I need to shut down Word or something? Why did it actually shut down the Surface?
Or stop altogether.
Did that kind of do something?
what is the
I don't want to.
It is totally still recording your presentation.
I
I don't know why it's not showing it up there.
Okay.
Uh,
If you want, we can. I could certainly give you a demo. We can tie me. If it's something you're interested in, I'd be very happy to set up a call with you and give you a demo of it. But it's.
I was curious, it looked very good.
Yeah.
Just
Oh, you saw a quick brief of it?
Yeah.
Well, just so it uses a lot of kind of really neat technology. It uses a lot of graphical ways to say how the message flows through the system and the different blocks. It also has components in there to be able to put scripting on it. So once I build up the whole application, I press a button, and then it'll actually deploy it as a Docker container that'll go out there that you can scale. The whole idea with my product is I set up something called a listener, and the listener actually listens for messages coming in. The listener expects two different things to be able to do anything with those messages. One is the device ID, and the other is the message ID. Once I identify those two pieces of data, I can identify the route through the system of how I need to process it. And the routes can do things as far as like doing decryption of the message. It can also pull data out of it. It can store that. It can run basic scripts on it. It can send messages to other devices. And all this happens by, just like I say, just kind of configuring at a high level, so you're not necessarily going in there and writing a lot of code to make that happen. So it's fun. Yeah, I'd love to talk to you about it if it's something you're interested in. But John thinks we need to get for beer, and I'm actually getting a little parched myself. So thanks, guys.
thank you.
All right, and this invite for tickets. All right, we have one giveaway here. We got a Raspberry Pi.
Yay!
No, didn't
Pick us
Who has ticket ending in 41? Or you want to say?
Go for it.
414. 414. 414. Going once?
Well, there you go.
All right.
Oh, careful.
Yep, so look at 110 IoT core for that. There you go. You're set.
Yeah, and actually, if you go to wherever you get the Raspbian image, there's an option there.
Yeah, you can get it up there too. Yeah, it's free to get started with.
Yep.
Be very
Cool.
careful
And
about the card you use.
Yeah. Make sure, you look at the specs for the SD card for it, the micro SD card.
Yep.
Yeah. Cool.
All right, so that's all we have for tonight. Appreciate everybody coming out. Join us next month. We'll be here the first Tuesday of the month, every month. We're still looking for more presentations throughout the year, so if you have any suggestions or any ideas, let us know. Please do follow us on Twitter and YouTube, and join the conversation on Meetup. So, thanks everybody.
Thanks for one beer.